It is really an honor to be here to introduce my paper. Here the six people are the following authors of my paper. So, uh, as everyone knows, searching and reusing existing code from the large-scale codebase can help developers complete a programming task efficiently. And during the software development, developers often spend 90% of their time searching some reusable code examples to save their development efforts. However, developing a satisfactory code search engine is challenging. As for code search, there are some early studies. In the early time, people always use the information retrieval techniques such as the Lucene-based model coders, Curl, and Google SearchNet. These information-based models simply treat the code and search query as plain text, as common web search engine, and miss the programming information. So others may use deep learning-based joint embedding techniques. These joint embedding techniques always embed code and query into vector spaces by two independent networks, and learn a joint embedding to align the two vector spaces. In spite of these deep learning-based joint embedding techniques and the information retrieval techniques, there are some limitations of them. First, as for the information retrieval models, their limitation is they fail to bridge the semantic gaps between programming language encode and language and natural language inquiry. And for the joint embedding methods, their limitation is they cannot fully capture the semantic correlation between the code and query. So, in order to address the limitation of the following early models, we proposed a new co-attentive representation learning model called Co-Attentive Representation Learning Code Search, and this can be called as COCCN. You know, the main architecture of our model is first, this model takes the commented code as model inputs, then it performs individual embedding on code and corresponding description, respectively. Where code components, there are three code components. For example, there are method name, API sequence, and tokens. They persist separately. Afterwards, the COCCN learns co-attentive representations. The main architecture of our approach can be separated as three parts. The first part is description embedding. So the description is can be seen as a natural language query. So we use the CNN to embed the description word vector matrix to the several description features and concatenate these features to a whole merged description feature matrix. And the second part is code embedding. The code embedding can be separated as three parts. The first part is the method name embedding. We use the CNN to extract the abstract features of the method name words, and we also use the CNN to embed the tokens. And third, we use the LSTM to embed the API sequence. And after embedding these three components, we merge them to a whole feature matrix called merged code C, and we put the matrix D and matrix C to our correlation to our co-attention mechanism to get a correlation matrix named F, and we apply the column-wise and row-wise max pooling to over the correlation matrix. Then we can get two separate vectors, and we apply the softmax function to these two separate vectors, and we can get two separate attention vectors for the code and description. Finally, we apply the dot product between the code and description matrix to their attention vectors. Then we can output two representation called description representation and code representation. Then finally, we can use these two representations to get their cosine similarity. And this is the whole architecture of our model. Next, we'll introduce our dataset. The training dataset, we're following the author of the model named DeepSS. We use the same training data as them. The training data is the commented Java method from GitHub repositories, which created from August 2006 to June 2016 with at least 1 star. And the testing data will use the 10,000 Java code query pairs. So next, I introduce my baseline models. The first baseline is DeepSS, the state-of-the-art model proposed by Google. It also uses 3 components of the code, and it uses RNN networks to embed them, and use MLP to embed tokens. For description, they use RNN to embed it, and after embedding, DeepSS use 4 separate max pooling operations to get their features, and it merged the 3 features to a whole code vector C, and finally it calculates the cosine similarity of the code and description. The next baseline model is the Co-CNN. Co-CNN is the model that incorporates the Co-Attentive representation learning to DeepSS with the same STM embedding as DeepSS. The third baseline model is the Cox-STM. The Cox-STM, the proposed model that replaces the STM model in Cox-STM by the CN model and use the same co-attention mechanism. Now I introduce my model effectiveness. You can see that Cox-CNN can achieves the MRR and record, which can improve DeepSS by 27.84% and 18.1% and 13.1% in terms of record. So it's the same as Cox-CNN versus the Cox-STM. And for the model effectivity, for training, DeepSS will use 50 hours, but our Cox-CNN only use 10 hours. For testing, the DeepSS use 1.2 and minus. And for Cox-CNN, we can use the least little time. And let's look at the impact of the 3 code features. The M represents for method name, A represents for API sequence, and T represents for tokens. You can see that We can draw a conclusion from this chart that it's necessary to use three code features together for model inputs, while the method name affects the effective most. Okay, that's the whole description of my paper. Thank you.